Okay, thank you. Okay. Are you able to see the screen? Can anyone unmute and just say yes if you're able to see the screen?
Yes, miss. Yes.
Okay, thank you. And I hope you watched the previous recorded video for the last week's tutorial. So today it's just the continuation for the 2 remaining questions. So as usual, I'll go through on the lecture slides on the operational side of the railway system or railway network. Then later we will look into the remaining tutorial questions, that is 8 and 9, the 2 questions that we left from last week. Okay. So in this particular lecture, the last lecture actually, we are looking at a few things: the station layout, platform, because all these are part of the day in, day out of the operational system of your railway network. Then we'll look into signaling and then how the railway operates in terms of operation. Yeah. So railway in terms of station layout, planning, what are the important parts of the railway system. So you can read a lot from this book. It's not very long, it's not a lot. You can easily digest. So I suggest you can read to gain more knowledge from this book. Then there are some objectives in station planning that are included already, that you want to promote attractiveness in appearance, free movement of passengers, safe evacuation in terms of an emergency situation. How do you evacuate? Because stations sometimes are closed, especially the ones underground. So access for disabled, there should be access for disabled people, access for emergency services, safe accumulation and disposal of crowds, reliable operation of train service, resilience to failure, also cost-effective investment. Okay, so these are among some of the objectives in station planning. So for a railway station, it's divided into 4 main core areas: for departing and arriving, information seeking and so on, transition area, where this is open for passengers as they transition into the boarding and aligning area. Then we have peripheral area, where boarding and alighting happens. This is usually controlled already. Only ticket holders are able to access into this area. The last but not least is the administrative area, which is for administration purposes. So other requirements, users, and comments, you can read it on your own. These details, you have to pass it on your own, just read through. Then moving on to platform. So we have 4 types of platform, but different heights of platforms can be categorized into 2. We have train platform height and train floor height. This is also similar with the buses and trams. So for trams, we have ultra low floor tram, low floor tram, high floor tram, and train. Very low floor, you see it's around this height, and the train is very high above the ground, 800 to 1200 millimeter. This is very high, so you need some sort of platform that is built higher than your ground level, so that it tallies with, it tallies with your train flow. So just now we mentioned there are 4 types of platform. We have bay platform or dead end. This is usually used for siding, but not as a main through platform. Then you have the second one, the through platform, where the train can actually go through the station. Then we have island platform, where you need to have some sort of crossing over to the other side. This is not connected to the main station building. The fourth one is side platform, which is usually facing outside from the station building. These are the general layout of the platform, of the 4 types of platform. Now let's move on to signaling. This is under operational signaling. If you follow the news, I think from last year in Malaysia, in KL, I think there was a collision in the metro system, sorry, not metro system, but the LRT system, and where 200 plus people injured on board. 2 trains collided because they suspected some sort of miscommunications, from the communication center. So the 2 trains were actually moving in opposite direction, and they were on the same track. So somewhere signal didn't work properly. There was some sort of miscommunication. So signaling is very important to ensure that the safety of your road users, of the people on board. Okay. So long distance train, they have drivers, and these drivers are the ones that control the train according to what the signal has been displayed. Similar as driving the car, you have to follow the traffic light. You have to obey the rules of the traffic light. So same case with these trains, you also have signals to control every now and then, because we only have one track which is shared by different trains. So therefore you need some signals to control the trains and to avoid what has just happened. So for signaling, the purpose is to communicate the information, the correct information, if I may say. Make sure that there is a safe distance between 2 trains, the front train and the first and the second train and the subsequent trains, because we know that a lot of train will be sharing the same track. So they have to keep a safe distance between the 2 trains. Also to keep the safe distance between opposing trains. We don't want something that has happened last year to happen again. And then to provide interlocking between points to make sure that conflicting movements are prevented and turnouts and crossovers are held in the required position. Then to provide adequate warning for the trains, particularly if it's sharing space with road users and pedestrians. Even though it could be fenced out, but sometimes you have to avoid, you can't avoid, especially in the crossing part. So if that part is shared, you have to provide adequate warning signs to warn of road users and pedestrians of the incoming and outgoing trains. Okay. Just now, we said that we have to maintain a safe distance or separation between following trains. Will also mean that it will help the train in terms of operation to run at the headways required that you need. Let's say if the train has to come at every 3 minutes or after every 5 minutes, that is the headway that we're talking about. So the signaling will actually help the trains to arrive into the station according to the timetable. Okay. In terms of signaling systems, we have three types: manual block signaling, we have fixed block, and we have moving block signaling. This moving block comes with communication-based train control. That means you can communicate with the train and see where the other trains are at that point in time using some sort of GPS or even Wi-Fi. Okay, but for the manual block, let's see. The manual block is manually done, but for fixed block, the signals are fixed at certain location. Let's say you want to control the train within a certain headway, then you want to use fixed block signaling. So by the time the train passes through that fixed point, then 3 minutes later, the other train has to pass through that point. But for the moving block, this one allows the train to move a little bit faster or slower by using communication-based train control. Let's move on. This is how they control the train actually. This one is the train stop mechanism to ensure that the train does not go over speed, or if the train does not stop in time, so this one will be activated to stop the train in case of an emergency. So another signaling purpose is to protect the train and warn the train, especially if it runs too fast or it doesn't stop in time, so this warning will be activated. So this one activates brakes in any train that is fitted with TPWS and has passed the red signal. So that means they have gone too fast over the limit or over the speed limit and over the point that they are supposed to slow down, but the train did not slow down, so this one will be activated to stop the train or slow down the train. Okay, moving on. So a moving block signaling system is essentially a high capacity signaling system because it's a moving block, so it will know the distance between trains continuously. So if you have the first train moving slow and the second train is about to catch up with the first train, so that distance will be communicated, either the first one to slow or to the second one to speed up a bit. So if the communication is to the second train, they will tell the driver to slow down a bit. So the distance between the two trains will be kept into a minimum safe distance always. So the minimum distance between trains must be long enough for a train to come to a complete stop. So if your first train is too slow, the second one is too fast, then the information will be communicated into the train. So the drivers of the train, they won't know if the train of the front is very fast, so they won't know. So they need some sort of communication to tell them from the control center. So if you look into this example, this illustration, this is considered as one block and this one is another block. So the distance between the two trains are separated by two blocks actually, so that it provides safety. For example, if your first train is moving and the second train is catching up, so you need to stop. For example, you need to stop the second train, so you need a certain distance because the train is very heavy, we know that. So it will take a long distance to come into stop. So you need these two blocks because they act as a safety block that you cannot have the train trailing too near to the other one. So the TPWS, the braking system, that is to ensure that the trains actually are stopped externally or automatically and externally. So if you look at this in this figure, so we have this train going at a speed of 160 kilometers per hour. So in a normal case, if the train passes by this point, it should slow down and come to brake here, stop at this point. But if the train goes over this and then hasn't stopped here, didn't come to a complete stop here, then the TPWS will be activated to stop the train, so that when the train comes at this point, it will stop. It will really stop. So this is the point where the out of control train is tripped by the TPWS to slow down the train, up to the stop. So you can see that you need 2 blocks for safety purpose. So signaling will also need to take into consideration the time taken for each train, not only to consider the time between 2 trains, but also the times other than other timings that involves in the train operation all at once. One is headway between the trains. How much time do you give between the intervals of 2 trains? If your service line, let's say you give it at every 10 minutes, you'll have 1 train arriving. That means for the entire hour, you have like 6 trains arriving at the station. That's actually the headways. Let's also look into dwell time. Once your train arrives at the station, your passengers will need time to get off or board the trains. So this is dwell time. And dwell time is affected by several factors: the type of train you have, whether it has a lot of doors, whether the doors are open, big and wide, or it's just one tiny door, the number of carriages you have in your train, how fast the mechanism of opening the door, and so on. And what are the passengers load? If you have high volume of passengers, then you need more time in terms of dwell time. So all that is actually affecting the dwell time. And it will also affect the operation of the whole train. So I've mentioned some of this already. Then we need to add in recovery time, is to enable the railway to accommodate typical delays that occur, because your train will definitely experience some times of delays. Sometimes it stops longer at a certain station, so you need to account for all that delays. This is just some information you can pass through. So part of your train operational side is to estimate the fleet size requirements. How many number of carriages are required? How many number of locomotives are required? Because all that will involve cost in terms of operational. So we will look at the fleet size requirement for locomotives and wagons for a heavy haul mining railway operation in our tutorial later. This is just an example. So with that, you have to work out the timetables. If you know, so if you are managing the railway station or railway system, so you don't only operate one line, you can have more than one line. So you need to work out some sort of timetable so that we know morning peak hour and evening peak hour, they can be different. So the loads usually is higher during the peak hour. So how do you manage that? So for peak hour, you can have shorter intervals. So every 3 minutes, you might have train coming, or every 5 minutes, you can have a train coming. But off peak, if it's not a peak hour, you can have maybe longer time, maybe after every 10 minutes, that is when another train is coming. So this has to be factored out in your working timetable and eventually transferred into crew rostering to see who is on duty. So drivers will be put into roster of 8-hour shift. They may start at 5:30 or 6, and they work 8 hours. Then they change to a new driver. Okay. So one thing actually leads to another. So you need to know the time interval that you want or the spacing between train that you need between peak hours and off peak hours in terms of timetable and crew rostering. So the working timetable is for the entire operation, not for individual crew member. For individual crew member, they will have their own duty roster. So this is a typical driver roster on a Sunday, and this is the station name. So where do they start? This is the departure time and arrival time. So where are they going to be and at what time? Okay. So operational side is a bit some sort of calculation to get all your things in place, but it's also common sense in a way that you have to think or manage a lot of things in terms of the fleet that you have. How do you put it to maximum use? How do you use it effectively? And how do you manage the human resources that you have, your drivers, your crew members, and so on? Okay. So is there any questions so far? Any question? If no question, then we will move on to today's tutorial, to the last two questions that we left out on the operational side. This is on fleet estimation. This is the impact of stopping trains. And the last question will be in terms of operation. So we'll look at it one by one. So question 8 is on high-speed rail, HSR, the impact of stopping trains at intermediate stations, all right? The question goes, at intermediate stations along the route of HSR, trains will pull off the main line and call at station on a refugee or passing loop. This will effectively allow non-stopping trains to overtake stopping trains at full speed. Okay, so A, what is the length of the refugee loop required given the following train and service characteristics? And B, what will be the design speed for the converging turnout from the refugee loop to the main line when the train departs from the station platform? So these are the characteristics given. The maximum train length is 320 meters. Your platform length is 340 meters. And your maximum speed through the entry turnout is 240 kilometer per hour. Let's go to the diagram and see this entry turnout. So if you have a line, this is your main line. Okay, let me just use this one, it's easier to see. If you have a line and you have to diverge from this line and go to another line, so this is actually your turnout point. This is where you turn out from your original line. Okay. So you have two turnout points. One is this, where the train diverges to either from the original line to another line, and another point is this one, where this is called converging turnout, where you converge back to your main line. So it leaves this line and join back to the original line. So if you're coming from this direction, this will be your diverging turnout point, and this again will be your converging turnout point. So it says the maximum speed through entry turnout is 240 kilometers per hour, where the diverging and converging happens. Where the diverging, because you're entering. And the design speed of the main line is 400 kilometers per hour. So that means when the train enter the turnout, they have to slow down to 240 kilometers per hour. And the main line has a speed of 400 kilometers per hour because it's catering for high-speed rail, so it has very high speed. For HSR, they can have 400 to 500 kilometers per hour, and the average acceleration and deceleration is given 0.3 and 0.5 respectively. Acceleration means the train stop at the station and then it start moving, going into the turnout and then into the main line. So that the acceleration rate is 0.3 meters per second square. And the average deceleration from the main line, you slow down to turnout, then to come to a complete stop, that is 0.5 meters per second square. And the distance from the platform to the fouling point on the refugee loop is 100 meters, and the turnout length is 200 meters. So this fouling point, what happened to this fouling, or what is the meaning of this fouling point? So the point at a railway switch or turnout beyond which cars must be placed to prevent their being struck by cars running on the line from which the switch diverges. So if you look into this diagram, if this is one train and this is another train, so the fouling point is actually here. So at this point, this is the point whereby there is a potential for the two trains to collide. If this is your main line and if the train passes here, so beyond this point, here, there's the main line train may collide with the refugee loop or the train on the refugee loop or on the turnout. This is what we call as the fouling point. So the distance from platform to the fouling point on the refugee loop is 100 meters. So if you go back to the diagram, not this diagram. So the distance from the end of your station to this point, this is your fouling point. This is actually your station. So from that edge of your station to the falling point, that is your falling distance. And it's 100 meters. And the turnout length has been given as 200 meters. Yeah, the turnout length is 200 meters. So question C, using above information under A, above, calculate the minimum headway between a stopping train and the following non-stopping HSR train, assuming no reduction in speed of the latter train. Allow 5 to 10 seconds for proving system functionality by computer software. Example, prior to the signaling system returning the refugee loop approach, turning out from reverse to normal. So that we assume 5 to 10 seconds, all right? So there are three parts in this question. First one is to calculate the length of the refugee loop required given the required characteristics. So let's move on to the first question, which is to calculate the refugee loop length. So if we put the question into an illustration, this is how it's going to look like. So you have these are your main line, and the speed here is 400 kilometer per hour, whether it's going in this direction or the other direction. These both main line have the same speed, 400 kilometer per hour. Now you have the station here. So to avoid delays to the train, any train that want to stop at the station, they will go into this they'll go into this lower lane or refugee loop, so that if the train behind them that doesn't want to stop at the station, it can just pass through using the main line and maintaining the speed that they're traveling with. That will not disrupt other trains or the whole operation. So we know we have introduced already the turnouts, the converging turnout. This one is the entry turnout. So it's the diverging turnout, and this one is the converging turnout if you move in this direction. And then you have this station. The station length has been given as 340 actually. Also, this is another station. So when the train comes along, it will stop at the station, and the train itself is just 320 meters. So I hope you're good with this explanation of the drawing or the setup. So the refugee loop is actually from A until the station, because this is the point where the train will come to a complete stop. Because if it enters here, it will slow down, come to a complete stop at the station. So how to calculate the refugee loop? Know that train must come to a stop at the station. So if it moves with 400 kilometers per hour, so it starts moving to slow down to 240 kilometers per hour, then move on and come to a complete stop at the station, which is 0 kilometers per hour. So from the given information, the maximum speed through a turnout at either A or B to the slower road will be 240, given in the question. So if you're coming from this direction, it will be A. If you're coming from the other direction, it will be B. So the speed to the slow road is 240. So this is actually at this point. When they move into this turnout, the speed will be 240 kilometers per hour. So distance to stop, so they're traveling at 240 here. So they need a certain distance for them to stop at the station. All right. So the distance to stop from 240 in meter to speed 0 in meters, we use this equation So they'll stop, so the final speed will be 0, but they started with 240, and because they're going to stop, you have to use the deceleration value. So you'll get 4,444 meters. So this is your distance to stop. So this means from here until stop, this covers 444 meters, 4,444 meters. And to calculate the total refugee loop length, and we must also know that for it comes to a complete stop, yes, but we have difference between the platform length and your train length. So your platform length actually exceeded your train length. So when you minus, you'll get a further distance of 20 meters. So 20 meters has remained here. So again, you have to add the falling point. You have to add this distance to the falling point, 200 meters on both sides. So the total length is your total distance covered to stop, plus the difference between platform and your train, plus the two falling point distance. Okay, so basically if you put into a drawing or better diagram, this is actually how it will look like. So when you turn in the converging turnout, sorry, the entry, the diverging, the length is 200, the turnout itself is 200. Then we know the falling point distance is 100 meters. Then you'll slow down and come to stop, further distance of 4,444 meters. And it will come to a complete stop here, but it has some allowance of the station. The difference between platform and your train is actually 20 meters. Then again, you have your falling point. Repeat of the other side, these two. So if you add all up, because your refugee loop starts from the falling point till this next falling point. So if you add everything, you will get this 4,664 meters. I hope this makes sense to you. Just know your refugee loop is from your falling point, from the first falling point to the other falling point. Yeah, so that is your refugee loop. You have to add all those distances to calculate your refugee loop length. Okay, so now we have to move on to part B, which wants us to calculate the design speed for the converging turnout. Because the entry turnout speed is given already, which is 240. So you have to design for converging turnout. Converging means as you go out from the refugee loop and converge back to the main line. So design that speed, okay? So not this side, this one is the entry and the speed has been given already, 240. So if you go to the refugee loop and you're leaving the platform and going to the main line already, so it wants us to design the speed at the converging turnout. Okay. So we know that the train, because it has come to rest, so it will start from rest at the station, having the initial speed of 0 kilometers per hour. So we need to know that speed at the rear of the train, because this will be the last point to clear the turnout. So we need the speed at the back of the train. We know that the train can be very long. So the maximum length of the train in this case is 320. So we need to clear that 320. Let's go back to the diagram and see. Let's say the train is resting at the station, and if it wants to go out, it will start from 0. Slowly, it will accelerate bit by bit to join back to the main line. So if you are here, this train, because it's very long, it will need some time to clear the 320. So it will need the entire train to clear from this point, the 320 train to clear from this point first and move into the main line. So you need the whole train. It means the back of the train also to clear out from this point. That is what we are talking about. So we know the turnout length is 200 meters. The total distance from the start point of the station. So it starts from 0 kilometer per hour. Platform less train length, that is 20, the 20 remaining distance. If we go back to the previous slide, we'll stop here. The train will stop actually here. The rear of the train will be here. So we have this difference of 20 meters. We have difference of 20 meters here. So plus 100 falling point. Then you have your turnout length. And then you have your train length, which is 320. So the train will need to clear a total of 640 meters to get back into the main line. Okay. So if you use this equation again to calculate the initial speed we have, which is 0, 2 times the acceleration we have, and the total distance we have 640, then we'll get the design speed to be 19 meters per second. So we know this is 20 plus 100 plus 200 plus the total train length, so that all of it clears the turnout. So it will cover the total distance of 640. Okay. Yeah, so you find your V, it will be 19 meters per second, equivalent to 70 kilometers per hour. So what does this mean? So you're just catering for a speed of 70 kilometers per hour. So your turnout radius cannot be very big. Earlier on, the entry turnout here will have to be designed with a larger radius because the entry speed we are given, it was 240. It was very high. But now when it enters the platform and leaves out, and we know that the speed, we just need 70 kilometers per hour. So you can actually design a smaller curve radius because it's only catering for a small speed of just 70 kilometers per hour. That's the implication of this. Only small turnout required, as this will be the maximum speed existing the station. For the other one, for the entry one, you need a bigger radius because you have high speed of 240 for the entry one. Okay, now let's move on to the last question at C. C wants us to calculate the minimum headway between stopping train and following non-stopping train. So what it means is that there is one train that comes into the station, it will stop, and the second train that arrives at this station, but it will bypass this, it won't stop at the station, it will just pass through the main line, continue to move without stopping at the station. So what is the safe distance between these two trains? What is the headway between the first train that stops at the station and the second train that does not stop or bypass the station? So what is the headway? We know that at point A, time for train to clear the turnout at 240 kilometers per hour, which is the maximum speed. Assume the length of the turnout is 200 meters given, and the back of the train must also clear the turnout distance. So you take your train length plus turnout, the total distance to clear is your train length. The total distance to clear from this main line at the time train enters here. So we want the whole train to clear out from this main line. So it will be this 200 plus the total distance of the train. So the distance traveled is the total train length. All of it has to clear plus the turnout length, okay? So it will be 520. 320 plus 200. So if you use this acceleration equation, so it will clear a distance of 520, and the initial speed entry is 240. And because you are decelerating to go back to the station, so you have to use the deceleration, then convert that into second, you'll get 7 seconds. So this is the time for that train that is required to clear out from the main line. So you need 7 seconds to clear the turnout. Then we have the braking time from 400 to stop. That will require 2 to 2 seconds. Then we add in for computer system to ensure line clear. It was given that we need to add 5 to 10 seconds. So the 3 items, you add them together. This is the total time between. It will be around 234 to 239 seconds, or you can round it off to 240 seconds. So it means the average headway for the train, if you divide by 60, it will be around 4 minutes. So what this means that the first train arrives, so the second train can only come 4 minutes later. So they have to be 4 minutes apart. If we put that into this diagram, sorry, this one. So from 400 kilometers per hour from your main line to enter into a turnout using these two speeds, you can calculate the time. You'll get 89 seconds. Then from time to clear the turnout, you get 7 seconds. And time to move back to the main line, or to get to a complete stop, you'll get 133 seconds. So when you add all this up and you plus the 5 to 10 computer time, then you'll get the same answer, 240. Okay. You add 89.7 and 133, you'll get 239, I believe. So if you, sorry, you'll get 229. Then if you add 5 to 10 seconds, you'll get 239. That means if the first train arrives here, then for safety purpose, the other train has to be 4 minutes away. In case of any emergency, if the second train is not able to stop, so you have that safe distance for it to stop. Okay. So I know it's a bit lengthy for this question, and you probably need some time to digest, but anyway, you can always look back at the tutorial, the solutions that have been discussed, okay? So that's all for question 8. So now we have to move on to question 9. Question 9 is on mining railway operation. And the question reads, a mining company operates a series of underground metalliferous mines that are located in steeply graded valleys. A new mine is to be opened in one of those valleys that will have an estimated output of 3 million tons per annum. A 150-kilometer line of a single track branch line railway is proposed to connect a new mine to an connect a new mine to an existing railway line at a newly constructed junction that carries other mining and freight traffic. The branch line will be designed with a ruling grade of 1 in 100 upgrade in the loaded direction and 500 meter minimum radius curves. The average speed of the train shall be 60 km per hour in the loaded direction and 80 km per hour in the unloaded direction. A. Estimate the average size of the ore train, including the number of ore wagons required, assuming 6 days per week operation and 50 weeks per year. So you don't work every day, you only work 6 days per week and 50 weeks per year only, okay? And estimate the number of AC diesel electric locomotives that will be required to pull the loaded ore trains. So first one is to estimate the number of wagons required or wagons required to move the material. And the second one, how many locomotives are required or how many engines are required to move these wagons. Assumptions: capacity of hopper wagons is 140 tons, whereby 25 tons tear, that is empty wagons, plus 115 tons of load. It can carry this amount of load. So if you total up, one wagon is 140 tons. And the wagon length is 15 meter per wagon. If you have 2 wagons, then it will be 30 meter, 3 wagons, 45 meter respectively, and so on. So the locomotive length is 25 meter and the locomotive mass is 200 tons. These are the engines and these are the wagons. The average loading time per hopper wagon from overhead surge bin at mine is 4 minutes per wagon. The average discharge time through unloading tippler at the port is 5 minutes per wagon. Allow 3 hours for checking train at unloading point, including refueling locomotives, and allow 1.5 hours for checking train at the load point. The maximum length of the ore train is 1.5 kilometer, and the maximum draw bar pull on the couplings will be 15,000 tons gross weight. So all these characteristics of your trains have been given. So based on this, you have to estimate the number of wagons and the number of locomotives required. You have to calculate the number of wagons required to move the material. The output, remember, is 3 million tons of materials per year. Okay. All right. And B, you have to calculate how many locomotives are required to move those wagons. The number of wagons that will be estimated. Okay. Hope you get the gist of the question. So let's move on into estimating the average size of the ore train, that is the number of ore wagons required. Okay. Okay. We know that from the question, back to the question, we need a 3 million tons per annum. This is the output, mining output. This is the amount of material that need to be transported. And we know that the operation is 6 days per week and 50 weeks per year. So based on that, we can calculate how many tons will be produced per day. If you divide the 3 million output, working in 6 days per week and 50 weeks per year, we'll get 10,000. This is the load to be carried, or the output that has been produced per day. So we get 10,000 tons per day of material that will be produced. This is the output per day. These ones material need to be moved from the mining to the unloading station, which is the port. So this amount of material has to be transported. You can see from the question earlier, average discharge time through unloading tipler at the port. So the discharge is at the port. You move from the mining station, you have to move every day 10,000 tons of material to the port, from the mining station to the port. Okay. So how do you move this? You have to use the wagons and the locomotives. So how many wagons do you need? How many locomotives do you need? That is what we need to determine. We know that the net weight of ore in wagons is 115 ton. It's given already. And total, yeah, you remember total of wagons, it was 140, but the wagon itself is already heavy. So if you put nothing, is already 25, but the load that you can, the iron ore that you can put in every wagon is only 115 tons. This is given in the question. So the net weight that you can put into the wagon is 115. So if you have 10,000, one wagon can take 115. If you divide, you can get 87 wagons needed. That is the number of wagons per day needed. So we need 87 wagons to carry 10,000 tons of iron ore. So we have 87 wagons in total. But you remember we have the limit in our ore train length. You remember it should be less than 1.5 kilometer. So we have to check this length. Okay. So total train length equals to 87 times one wagon is 15 meters. You remember it's given in the question. Upper wagon length is 15 and locomotive length is 25 meters. So 87 wagon, one wagon is 15, and plus this number 3, it's just an assumed value. We just assumed at this point. For example, we want to use 3 locomotives. It could be 2, it could be 3, it could be 4, or any other number. So this will be determined in part B, in question B, okay? But at this point, we just assume 3 locomotives, and every locomotive is 25 meter each. So if you total up, it will be 1.375 kilometer, is less than the 1.5 kilometer given, so definitely it's okay. Okay. So at this point, we have to check for the average train cycle time to see whether we need 1 train or more. If we need 1 train per day or more than 1 train, because at the end of the day, you need to move 10,000 tons of material in 1 day. Okay, every day you need to move 10,000 materials. So to check that, I have put the information in this diagram. We know that at the mining station at point A, you need to load the iron ore into the wagon, and the loading time has been given as 4 minutes per wagon, and that is not inclusive of checking the train, which will also take 1.5 hours. And after it has been loaded, so the train will move from point A to point B, and because it's loaded, it will move at a slower speed of 60 kilometers per hour to move to the port. And when it reaches the port, unloading will take place. And the unloading will take time of 5 minutes per wagon. And after that, you have to refuel the train, and it will take 3 more hours. Then once unloading has been done, the train will then move back to point A, to the mining station. And because now it's empty, there's no load already, it will move at a faster speed of 80 kilometers per hour because now it's empty. So now what we need to do is check the average cycle time from the loading station to the unloading station and back again to the loading station, inclusive of all the checking times and refuel time. Okay, so you have to add everything. So if you calculate the cycle time, you'll have your loading time is 4 minutes per wagon. We have 87 wagon, that is 348 minutes. The checking time was 1.5 hours, that is 90 minutes. Run time from A to B, so in 60 kilometers per hour, you have to take your distance, divide by your speed, you'll get 150 minutes. And then the loading time is 5 minutes per wagon. We have 87 wagon. It will give 435 minutes. Then you have check, train, and refuel. It will take further 3 hours, which is equivalent to 180 minutes. Then the run time from B to A at 80 kilometers per hour. So your distance divided by your speed, you'll get 112 minutes. And then the total time, if you add all this up, it will be 1315 minutes, equivalent to 21.92 hours. Which is less than 24 hours. Therefore, this means that you'll need the journey from A to B and back again to A. All of this needs approximately 22 hours. So so a day is sufficient, and one train is actually sufficient to move the material, 10,000 material, from point A to point B and back. Since it's less than 24 hours, so one train is actually sufficient to move 10,000 tons per day. Okay, that is part A. So the number of wagons required is 87 wagons, and 87 wagons be moved with just one train at one shot. You don't need to break it at 2 trains. Okay, now let's move on to part B, where it needs us to calculate the number of diesel electric locomotives required. So just now we assumed 3 locomotives in our calculation for part A. You remember? You remember here we assumed 3 locomotives, but this is just an assumption. So we have to really calculate whether it's 3 or not. So now we need to determine that under this part B. So under part B, what we need to do is to determine the tractive effort to haul or propel a train in the most adverse condition. So the most adverse condition is actually when the train is going uphill. Earlier on in the question, when we look into the question requirements, the branch line will be designed with a ruling grade of 1 in 100 upgrade. So this actually determines the power of your train, the limitation of your train. Okay. So if your ruling grade is too steep, your train will face some difficulty in climbing up. And your minimum radius is given as 500 meters. Okay. Now, where do we get this kind of information from? Go to the PDF file. Together with the tutorial, there was other PDF file that was given, this one. So from this part, in particular, we look at the technical detail, and the starting tractive effort is 200,000 pounds. Okay. This is the starting track. This other is not that important. So we just look at this tractive effort. Tractive effort is to hold the train in most tractive. So we look at all these characteristics, all these. the starting tractive effort we just looked is 200,000 pounds. The other information were not that necessarily. Now let's move on. So the tractive effort is the sum of train resistance, which is 2.2 kilogram per ton, grade resistance, which is 10 kg for every 1% of grade per ton. Curve resistance is 0.3 kilogram per degree of curvature per ton, and train acceleration is 5 kg per ton. So these are the factors that govern tractive effort. How effective or what is the effort required to move the train? The resistance from the wheel track, from the grade, from the curve, from the acceleration. Yeah. Okay. So if you add all this, that will be your tractive effort. So we need to account for train weight and locomotive's weight. So the train resistance is 2.2 kg per ton. So we have to calculate how many tons do we have for the entire train. We know that there are 87 wagons and each wagon is 140, 25 empty plus 115 when for the loading. Total is 140 plus number of locomotives. So we assumed 3 locomotives, which is 200 ton per locomotive. So if you add all this up, you get about 28,116 kg. That is your train resistance weight. So grade resistance weight is actually 10 kg per 1% change in grade per ton times how many tons you have. So the tons actually obtained from here after adding everything, your wagon and your locomotive, and it's 12,780. So where do I get this 1%? It's actually given in your question. It was stated in your question. The ruling grade is 1 in 100. That is 1%. 1 in 100, it means 1%. Okay, so it's 1% when you times with the total weight, it will be equivalent to 127,800 kg. Then we have curve resistance weight, which is 0.3 kg per degree of curvature. So this formula for degree of curvature is actually obtained from your road engineering. And your radius is given as 500, then multiplied again by the total weight. It gives you 13,396 kilogram. Then you have your train acceleration, that is 5 kg times total weight. So it will give you around 233,212 kilogram. So if you total up everything, you'll get your tractive effort. It will give you around 233 kgs. You convert that into kilonewton, you get around 2285 kilonewton. So we need the train or the locomotive need to be able to hold the train or move the train with this much power. This is the effort to move the train. Okay. This is the force required to move the train. So for this model, the starting tractive force from that attachment, you remember the one we referred from the attachment, it was 200,000 pounds. If you convert that to kg, it will be 90,718 kilogram. And if you convert that into kilonewton, it will be 889 kilonewton. So the number of locomotives required this means one locomotive can move 889 kilonewton. The effort it has is 889 kilonewton. But right now, just now we calculated this is the total effort that we have. When you divide by the effort of one one wagon, one locomotive, so you need 2.57 locomotive. Approximately, you need 3 locomotives, okay? So that means our assumption earlier of having 3 locomotives, it was actually correct. So 3 locomotives are actually required. So sometimes for this type of question, you might need to do it more than once, especially you see, there is a note here. It may be necessary to do a number of iterations to obtain the optimum operational cycle time. So if you calculate here and you didn't get 3, maybe it was 4 locomotives, so you have to recalculate back again. You do a little bit of adjust in terms of tractive force. You see, you need to recalculate in terms of length of your, yeah. So if you change here number 4 to 4 so you have to change to 4 locomotives and recalculate back and see if it satisfies the length. Okay. So if you determine that you need 4 locomotives, you have to change this to 4, calculate back again, recalculate again, and see if it fulfills the 1.5 kilometer length. Not only that, you also need to recalculate back your tractive force, because 4 locomotives will change the tractive effort, or the resistance will change, okay? You have to readjust again, everything here will change. So it's a trial and error or iterative process. All right. So for this entire operation, to move the 10,000 tons per day, every day, we need 87 wagons and per train, and we also need 3 locomotives are required to move 87 wagons. Okay. So for that, it is the last part of the tutorial. So is there any question? Is there any question? How to assume locomotive? Yeah, you can also assume 2, so that later when you calculate, if it's not 2 again, you have to change back. You can assume any number, 1, 2, 3, 4, just assume any number, but if you assume that number, it has to satisfy the length given. So if the number you assumed, it satisfies the length given, you can move forward with that number. But later when you calculate back and it's not the number of locomotives, so you have again to change, because your tractive force will also change. Okay. Is there any other question? All good, okay. Okay, if there is no any other question, then all the best for the rest of your semester. Then if you have any question, you can drop me an email. Then let's end this tutorial here. Bye and take care.